Okay, hello everyone. Welcome to ME304 Machine Design. We're doing a compound reverted gear train this time. You can read this problem: 48 to 1 increase in angular velocity from the input gear to the output gear while maintaining minimum diameter pinions. You also have to go through and get the diametrical pinch meeting these conditions and list all assumptions that we make. Alrighty here. So, jumping into this problem. If you're not familiar with the compound reverted gear train, basically what it is it's a gear here and another gear here, which goes over here to a smaller gear again, or a larger gear, depending on how you're going through and increasing or decreasing stuff. And it's like that. And then these two shafts have to align perfectly. So these gears have to meet the reduction ratio or the increase ratio that we want, while at the same time remaining aligned right here. Okay. So we're looking for a 48 to 1 increase in speed. So if we're doing the using the rotational rates in order to get the ratio, E is going to equal N last all over N final is equal to 48. And if you want to look at this in a different way, I'll break up the fraction. The last gear has to rotate 48 times. This is F. The last gear has to rotate 48 times to every one rotation of the first gear. Okay, so since this E, which is equal to 48, is greater than 10 but less than 100, you're going to use two stages, and that basically means two sets of gears. So this would be one set, and this would be another set. If for some reason this reduction was a little bit higher, 100, reduction was higher, you might need 3 gear sets, and you should have been introduced to these approximations or these limits within your class. So I'm not going to go into too depth of those in the other variations. But so yeah, two sets right here. A set is basically just one gear and one drive pulley and one receiving pulley. Okay, so we need an exact solution. What you have to do is take 48 and find the two smallest factors that will create 48. So if you look at this right now, n2 over 3 would equal 8, and n4 over 5 would equal 6. Because the two integers, 8 times 6 is equal to 48. And that's how you start on the exact solution. You find out this little ratio, n3 and 5. And I'm just not being able to write this. Alright, so then we're going to assume that we have a pressure angle of 20 degrees, which is standard for almost all gears. K is equal to 1, and M is equal to 8. Okay, now in order to find out what the ratio is that we need for the second gear, if the very first gear is 8, what is the ratio we need for the second gear in order to meet an 8 to 1 ratio? Okay, so we'll use NP is equal to 2K all over 1 plus 2M. 1 plus 2M times sine squared of the phase angle, or the pressure angle, times M plus square root of M squared plus 1 plus 2M sine squared of the phase angle. Alright, so this is the equation we're going to use, and this NP is basically the second gear. So if this first gear has 8 teeth on it, like we're setting right here, because this is the smallest integer, what does this gear need to have in order to meet the ratio? Okay, so then, alrighty here. So N3, using this and subbing in 2, 1, and 20 degrees, if you use K is equal to 1, phase angle is equal to 20, and M is equal to 8, and you sub them into this equation, you'll get NP is equal to 17 teeth. And this is going to be equal to N3. And let me label this. This is N2, N3, N4, and N5. The reason we start at N2 is because N1 is considered the power plant for the motor. So if you had a motor out here, this would be considered N1. So if you had the rotational rate of the motor and you had to transfer it through there, that's what this notation is about. Okay, so in order to get the ratio of 48 to 1 that we want, we're going to start out with a gear with 8 teeth going into a gear with 17 teeth. So N3 has 17, N2 has 8. So these are the smallest gears we can possibly make and still meet the ratios because they're the two smallest factors that we can use to get 48. Okay, now for a compound reverted train, there's a condition that we need to use of N2 plus N3 is equal to N4 plus N5. Okay, now the reason for this is the fact that since N2 is directly related to pitch and diameter, you can basically go through and consider, if you were considering this N as a diameter right now, if you were to reverse everything, you could say, well, the diameter of this one plus the diameter of this one has to equal the diameter of this one plus the diameter of this one in order to make these two shafts align. So that's where this relationship comes from. Alrighty then. So then, using the ratio that we have of N4 over N5 is equal to 6, well that means N5 is going to equal N4 over 6, using this up here. So if we go ahead and take this little equation right here, solve for N5, then you get N5 is equal to N4 plus 6. So this is all going to equal 7, 6, N4. Because you replace N5 with N4 over 6, and then you add 6 over 6, and you get 7 over 6. Okay, so then, putting in the ratio for the teeth that we have 17 teeth and 8 teeth. So if we go, oh wait, I'm sorry, I made a mistake. Yes, this up here, where was it? Right here. This ratio is not the number of teeth. I was saying it was the number of teeth. This is just the gear ratio. Once you have the number of teeth that you can get for N3, you go ahead and N2 is going to equal 8 times N3, which is going to equal 8 times 17, which is equal to 136 teeth. So N2 is equal to 136 teeth, and 3 is equal to 17 teeth. So that's the reduction right there. I apologize. The notes that I have for this problem are not very good, so that was a little bit unclear. But yes, these are the gear ratios. Once you have this ratio, you use this equation to find the first, the gear number of teeth for the second gear. Then you use that ratio in order to find the number of teeth on the first gear. Then you go through into the compound reverted train, use this equation, change this up so that it all has just one single variable I have to solve for. Get this here, and we have 17 plus 136. Let me double check something here. I think there's another error in here. No, that's okay. Is equal to 76. So N4 is going to equal 131.1 teeth. Well, there's no way to have a fractional tooth, so we have to normalize this problem in order to get an even integer number of teeth. This has to be an integer number for a compound, or for any kind of gear set, actually. Usually you can kind of round up or something, but in this case with a compound gear, if you round up, that means you have the wrong diameter gear tooth and the shafts do not align. So you have to have integer values when you're working with compound reverted sets. So then, going ahead and normalizing the problem, basically what we're going to do is we're going to change the numbers a little bit so that they're all even integers. Normalize. Alrighty, so if we have N2 equal to 8, then N2 plus N3 is going to be equal to 9, following our gear ratio. We're going to go ahead and go backwards a little bit and just say, okay, well, what if we have the pure ratio of N2 equal to N8 right here? Instead of just considering 8 the ratio, we're going to consider it the number of teeth, basically. So if we do that, and we continue on with this equation, put in the other side of it, we'll have 6n5 plus n5, and this is again using this equation right here, solving for n5, or solving for n4, which is 6n5. Okay, to do that, that's equal to 7n5, normalizing the problem. So then n5 is equal to 9 7, just like that. And this is where this one's equal to 8, this one's equal to 1. There we go. Okay, this is just to get the ratio that we kind of need, again, a little bit. So, using a multiple of 7, in order to get this an even integer value, we have to get rid of the 7. So we have to multiply it by 7. So finding a multiple of 7, multiple of 7, which is greater than or equal to 17 teeth. Now, at 17 teeth is because earlier in the problem we established that NP has to be 17 teeth by this equation. Now, we need to find the multiple of 7, which gives us a number greater than 17, because if we're less than 17, we don't have the gear ratio that we need. So greater than 17, well, in this case, N3 is then going to equal 21. So we're going to make N3 equal to 21 teeth. Then, using our ratio of 8 to 1, N2 is going to equal 21 times 8, which is equal to 168. And you can visualize this for a second here. Let's just get a gear in here. We've got N2, which is equal to 168, and N1, N3 equal to 21. And this makes sense because we wanted an increase in angular velocity, which means basically you have to go from a large gear to a small gear. So this is making sense so far within the problem, because this has to have a reduction somewhere in gear size. The next one is going to have a reduction in gear size somewhere. So we're going to end up with a larger gear over here, and then another smaller gear coming out like that, and connecting these over straight like that. So this is making sense so far. So it's good to do these visuals once in a while just to make sure you know what you're doing and where you're headed. Okay then. So then, going back to our reverted gear equation again, we've got N2 plus N3. This is going to equal 189, adding up 168 and 21 up here. This is going to equal 7 N5. We're basically just working backwards through this equation now. We got N5 normal, so we've got this normalized, all the equations normalized, so that 7 will disappear as we go through this equation. This is equal to 7 N5. So then N5 is going to equal 27. Okay, cool. So then for that to equal 27, N4 is going to equal 27 times 6, which is equal to 162. So now we have all our gear numbers, and if we go ahead and say diameter is equal to the number of teeth over pitch, and we have a pitch of equal to 3 teeth per inch, then going ahead and listing these out, N2 is equal to 168, the diameter of 2 is going to equal 56, N3 is going to equal 21, so then D3 is equal to 7. Then N4 is going to equal 162. N5 is going to equal 27. And D5, D4, what the heck did I do? D3, D4 is equal to 54, and then D5 is equal to 9 inches. So then if you add up 56 plus 7, well, that's going to equal 63. And if you add up 54 plus 9, 63. So their diameters are the same, so that they align. In a gear train, you have the pistons or the shafts all aligned, and the gears have the reduction ratio that we wanted because we went through and normalized the problem. And that is how you design a reverted gear train.